Hey Tim, it's Raymond. Of course, you knew that. But anyway, so I really appreciate you giving me the opportunity to do this. I'm gonna do the best I can. I've got Jason's presentation here on the screen, and I'm gonna go ahead and start it off and go through it. So uh, we'll see what we can get out of this. All right. So this is Group 7, Raymond Curry and Jason Zhang, doing the spin architecture ECE 443 final project. So in this presentation, we're going to go over the abstract RTL that we've developed, some of the architectural points, the concrete RTL. We're going to talk about our controller design, and then a little bit of VHDL that we were able to code. So what we've got here is our abstract RTL. We did all 30 instructions, just like everyone else did. So the abstract RTL is what you'd expect of it. So I won't spend too much time on that, but it's there for your view. So our instruction format, what we did for our instruction format was we set up a 16-bit instruction with the last 8 bits being for the opcode, and then the middle 4 bits being for register X or register Y, and then the first 4 bits being for register X. So pretty straightforward. This allows us a ton of space. It actually, if you look, it's not here. Let's go back one. It's actually right here in the presentation. I'm going to pull this over just because Jason left out a lot of stuff. Right here you'll see that the controller is the last 5 bits, and the first 3 bits were the ALU. That's a relic from what Mike wanted us to do. So we just left that because it was already in there. So anyway, so 5 bits for the control for the opcode. Right here, 1, 2, 3, 4, 5, and then the first 3 are for the ALU stuff, but we didn't end up using those, so really it's just 5 for the opcode. So that brings us on to the opcodes themselves. We organized them as you'd expect, just sequential order as they came from the what's the word I'm looking for? As they came from the ISA. There you go. Sorry. So they came from the ISA, and that's the way we listed them. 5 bits, and that's about it. So the CCR is flags for the 0 flag, which indicates that the result of an arithmetic or logical operation was 0. The carry flag, which enables numbers larger than a single word to be added, subtracted, and by carrying the binary digit for less significant to least significant of more significant words needed. So the sign flag over here, and which indicates the result of a mathematical operation, is negative. The overflow flag is V right here, which was going to indicate the signed result of an operation is too large to fit in the register width using what is it? 2's complement representation. And the interrupt flag, of course, indicates that an interrupt is currently alive, and or that the currently executed code is part of an interrupt routine. So that's the CCR. The architecture, as most other people's architecture is a simple 2-bus design with direct access to the ALU operands, the memory, and the register file. The added complexity of an architecture with 3 buses was determined that it's just not worth the performance increase, and the single bus is just not enough. It wasn't what we wanted. So the adder is attached to the program counter so that it's a means of incrementing the PC without using the ALU, and it also reduces bus traffic. We added register C as an inherent location for the ALU outputs. Having that there eliminates the need for a destination register in each instruction. Bus A carries data, so let me pull up this image here. Bus A carries data, and bus B, bus A carries data into the register is what I meant to say, and bus B carries it out on most opportunities. So otherwise, it's 16-bit general purpose registers, and that's about it. So let's see. The concrete RTL is, as you'd expect, just like everyone else's, more or less. It's there. That's what that is. Oh God, this is a presentation. All right. So the controller design. The controller. That was kind of the last area we got to. We got to a little bit of VHDL as well, but the controller design is comprised, as you'd expect, of signals generated from the control sequences of the RTL for the entirety of the ISA. So to begin the design process, we created a port map for each subsystem, and then the control sequence for each instruction listed all the strobes and gates, which causes the data to be released and latched to perform the register transfers. So you'll see all of these control signals reflected in our VHDL as far as we got. So let's take a look at some of the VHDL. So the ALU, I gave it a swing. I've got you can see some of the stuff's starting to come in here. So these there's plus, minus, negative, multiplication. Let's see here, anding, ors, and knots, and shift left, shift right, shift left logical, shift right logical, shift right arithmetic. So you got all of those. That's as far as we got. There's definitely a couple left out. I took a swing at the memory address register, so there's a little bit of stuff here that's just the outline, really. Technically it's working, but I'm sure later on we would add more to this. The memory data register, here it is as well, 16-bit, all of that, as you'd expect. Starting to call in, here's tri-state. Later on we'll see that I coded up the tri-state. There's the end of it. Program counter, put that in, and then tri-state that I put together from project or assignment 1 or whatever it was at the time. And then this is the ending to the presentation. Dear God, I just looked at this and, well, it's almost true in a way. So anyway, that's that. Let me know if you have any questions. Shoot me an email. I really, really appreciate you giving me this opportunity. So thank you, and I couldn't get these points out without your, I couldn't get these points back without your generosity. So thank you. Let me know if you have any questions, and it was a great semester. You're the best. All right, take care.